Now on to question 4. Fuses are sold in packets of 15. Each packet could contain faulty fuses. A large number of packets are tested for faulty fuses, and the mean number of faulty fuses per packet is found to be 1.2. State the parameters of a named model that would be most suitable to determine the probability of a fuse being faulty. So this is obviously a binomial distribution. There are two possible outcomes. So a fuse could be faulty or not faulty. And we have a finite number of fuses in the packets, and that's 15. So the binomial distribution where n is 15, and the probability, where we don't know the probability of a fuse being faulty as yet, so n is 15, and the probability of a fuse being faulty, that's p. Now to get p, the probability of a fuse being faulty, we know for the binomial, the mean is equal to np, and the mean, we are given the mean to be 1.2. So 1.2 equal n is 15. 15 times p. So to find the value of p, we divide both sides by 15. So 1.2 divided by 15, that's 0.08. So p, the probability of a fuse being faulty, is 0.08. Show that the variance of the number of faulty fuses in a packet is 1.104. So the formula for variance, so variance is np times 1 minus p, and we know np, well, we know n is 15, p is 0.08, which we just found, and 1 minus p is 1 minus 0.08, so that's 15 times 0.08 times 1 minus 0.08, that's 0.92, and this works out to be 1.104. Determine the probability that a packet contains two faulty fuses. So it's a binomial, so the probability x equal to k is n choose k, p to the k times 1 minus p to the power of n minus k. So substituting, so remember each packet has 15, so 15, n is 15, so 15 choose, we're looking at 2, so 15 choose 2. P is 0.08 to the power of k, which is we're using 2, times 1 minus p. So remember p is 0.08, so this is 1 minus 0.08, that's 0.92, to the power of n minus k, 15 minus 2, that's 13. And I put this in the calculator. This works out to be 0.2273. Part B, a discrete random variable x has the following probability distribution. Calculate the expected value of x. So E of x is a summation of x times the probability x equal to x. So summation, so 0 times 0.01, that's 0. Plus 1 times 0.3, that's 0.3, plus, so the x values times the p values, so 2 times 0.3, that's 0.6, 3 times 0.1, that's 0.3, and 4 times 0.2, that's 0.8. We sum these values, and we end up with 2. Calculate the probability that x is greater than or equal to 1. So for x greater than or equal to, so that's from all of these parts, x is 1 or more, that's 0.3 plus 0.3, so that's 0.3, 2 times 0.3, 2 of them, plus 0.1 plus 0.2. And that works out to be 0.9. Or we could have just said 1 minus 0.1. Question 4, part C. The continuous random variable x has a probability distribution f as shown on the diagram below. Calculate the value of k. So the thing about this distribution is that the area under the graph, the area representing the total probabilities, of course, must be equal to 1. So to get the area, I must break up this into, it's a trapezium, so I'm going to break it up into a triangle and a rectangle. So the area, the total area would be area of a triangle plus area of a rectangle. So the triangle is half base times height. So it's half. The base, that's 1. The height, that's 2/5. Plus area of the rectangle, length times width. So the length here is from 1 to k. So that's the length is k minus 1. And the width, which would be the height, that's 2/5. And of course, one thing we can do to, let me just first expand. So so that's 1/5 plus expand this. So this is 2/5 k minus 2/5 equal to 1. So we can group like terms. So we can 2/5 k equal to 1. Bring this over, that's positive 2/5. Group the 1/5 also, that's negative 1/5. So which means that 2/5 k is equal to 1 and 2/5 minus 1/5. So that's 1 and 1/5. So this is 6/5. And if we can times both sides by 5, we end up with 2k equal to 6 times by 5, both sides, 2k equal to 6, divide both sides by 2, k equal to positive 3. Part 2, show that the probability that x is greater than 1 is equal to 4/5. So greater than 1 would be from here, from 1 to k. So greater than 1 would be the rectangular part. So greater than 1, we're going to work with the probability by finding the area of the rectangle. Since the rectangular section starts at x is 1, so the probability x is greater than 1 is equal to the area of the rectangle. So the rectangle, again, is k minus 1 times 2/5. But we know that the value of k is 3. So k minus 1, that's 3 minus 1, that's 2 times 2/5. And we get our 4/5. Question 5. The length of time x between planting and germination of a type of tomato seed is believed to have a normal distribution with mean mu and standard deviation sigma. A random sample of 30 such seeds was planted under identical conditions, and the length of time between planting and germination was measured. The following totals were recorded. Calculate the unbiased estimate of the population mean, mu. So the unbiased estimate would be same as x bar, and x bar is sum of x over n, and sum of x is 240. N is 30. N is 30. So 240 divided by 30, that's 8. Construct a 90% confidence interval for the mean length of time it took for this type of tomato seed to germinate. So confidence interval, the confidence interval, CI for abbreviating, is x bar plus z alpha over 2 times sigma over root n. Now we do not know the standard deviation sigma, but there's a formula for that. Let me just calculate sigma. So where is sigma? That's a standard deviation. So standard deviation is square root sum of x squared as a formula minus sum of x all square over n all over n minus 1. So the formula for standard deviation. So sum of x squared, we know sum of x squared is 2088. So 2088, sum of x was 240, so 240 square over n, which is 30, over n minus 1, which is 30 minus 1, that's 29. So this works out to be square root of 168 over 29, which works out to be square root of 5.793, and that's 2.41. So the standard deviation is 2.41. Find our confidence interval now. So remember x bar, that was 8 plus or minus. To get the z value, we're asked to work out a 90% confidence interval, so we can use our z table to get the corresponding z value for the 90%. Now, something we can do to get the z value. So 90%, that's 90 over 100, that's 0.9. So we add 0.9 to 1, that's 1.9. And we divide 1.9 by 2, we get 0.95. Now the z value is not 0.95. So we look for 0.95 in the z table. Let's go to the z table. So we look for 0.95, or the closest value to 0.95. So 0.95, that's here. 0.9495 is also here. So 0.95 is somewhere between these values. So the corresponding z value here, that's 1.64 or 1.65. I'm going to be using 1.645. So I'm going to use 1.645. The average of the two values there. It's the standard deviation. We just found it to be 2.41. So 2.41 over root n is 30, is over root 30. So this works out to be 8 plus or minus 0.724. So to get the confidence interval, we add and subtract 0.724 to 1 from 8. So I'm out of space, so I'll just squeeze it here. So if I add, it will be 8.724 for the upper limit. And the lower limit, I subtract it point from 8, I end up with 7.276. So this would be my confidence interval. 50 random samples of 30 tomato seeds are taken, and a 96% confidence interval for mu is found for each sample. Determine the appropriate number of intervals that will contain the population mean mu. So the number of intervals is simply n times the confidence interval, which is 96. So in this case would be n, which is 30, times, and the confidence interval is 96%, that's 0.96. So we end up with 28.8. That's approximately 29 intervals. A manufacturer claims that the mean mass of certain type of fab soap produced is 115 grams. A random sample of 21 such fab soaps have a mean mass of 110 grams and a standard deviation of 7.4 grams. Test at the 5% level of significance the hypothesis that the manufacturer is overstating the mean. State the appropriate null and alternate hypotheses for the test. So the null, we're indicating using H subscript O, and the null is that the mean, the population mean, is greater than or equal to 115, and the researcher is claiming that it's not. It's actually overstated. So the alternate hypothesis, H subscript A, is that the mean is actually the opposite of that. So we're saying the mean is being overstated. So he's claiming the mean is less than 115 grams. And we'll be using what we call a t-test. And of course, we use a t-test. If you notice, the variance for the population is unknown, and also the sample size is pretty small. So the sample size, a small sample size 21, sample size less than 30, and the population variance is unknown. Hence, the appropriate test, of course, would be the t-test. Now, the critical region, the critical value. So remember, we're using level of significance alpha as 0.05. So we go to our t table. So, but we also need degree of freedom. So the degree of freedom is n minus 1. N was 21, so the degree of freedom is 20. Alright, so we can get our critical value. So the critical region. Let's go to the table. So here's our t distribution table. Degree of freedom to the furthest left, column to the furthest left there, n minus 1, which would have 20. So 20, and level of significance was 0.05. So we look at 0.95 there. So the corresponding critical value here is third value there in the column, 1.725. So the critical t value is 1.725. And since it's a left tail test, so critical value t value plus or minus 1.725. Of course, there'll be a left tail test or a one tail test. So the critical value, let me just draw the critical value region there. So if I have my right there, t value, so the critical value t, of course, in left tail should be negative 1.725. So any value that's less than negative 1.725 is our critical value, is our critical region. So critical region. Any value left of negative 1.725. So t is less than negative 1.725, since it's a left tail test. Calculate the value of the test statistics, that's t. So now the formula for t is x bar minus mu over standard deviation over root n. So x bar was, so let's look at the question again. So from the sample mean was Standard deviation 7.4 and the sum and 110. Alright? Mu was 115. So it's 110 minus mu, which was 115, over S, and S was 7.4. Was it? S was 7.4. 7.4 grams, so S was 7.4. Over root N, and N was 21, so over root 21. So this works out to be -5, and the denominator is 1.615. So our t value is -3.16. Test statistics, -3.1. Using 1 decimal point. And the conclusion, so since the t value, the test statistics, of -3.1 is less than critical value of, and remember critical value was -1.725. So our calculated test statistics falls within the critical region. And our critical value was -1.725. So we're going to reject the null and conclude the alternate, and conclude that the population mean is actually, as alternate, is actually less than 115. Hence, the mean is being overstated. So what the manufacturer is claiming, 115, the researcher conducted his research and found out that the sample chosen was 110. And based on the t-test, that's enough evidence to conclude that this mean of 115 is being overstated. The following contingency table summarizes the responses of a random sample of 500 prospective voters to a survey on voter preference for 3 candidates, P, Q, and Z, contesting a general election. A chi-square test is carried out to determine whether there is an association between the age of the voter and the candidate preference of the voter. State the null and alternate for this test. So the null hypothesis is obviously there's no association between the variables, and the variables are, here are the variables, age of the voter and candidate preference. So there's no association between age of the voter and the candidate preference. And the alternate is just the opposite of that, which is there is an association. H subscript A, there is an association between age of the voter and candidate preference. Calculate the expected number of voters who are 60 years old and prefer candidate Q. So I want the expected value that's for over 60 and candidate Q. So for over 60 and candidate Q, for over 60, here's the over 60 category. Candidate Q is a candidate Q category. So look at where these two collide. That's at 113. That's at 13. So for the column for candidate Q, the total is 186. And for the over 60, the total is 81. So we multiply the totals. 186 times 81 divided by the grand total of 500. So 186 times 81 over the grand total of 500, and that would give us 30.132. Calculate the chi-square value. Calculate the chi-square value for the total number of voters who are 60 years old and who prefer candidate Q. So the chi-square value for that will be expected minus observed square. That's the formula for the chi-square over expected. So the expected for these two categories would be 13. So 13 minus 30.32. So the actual value, so the observed value is 13, and the calculated expected value is 30.132. So 13 minus 30.132 all square over the expected, which is 30.132. So that gives us 9.74. Determine the critical region of the test at the 5% level of significance. So let's look at the chi-square table. Now before we go to the table, we need to calculate the degree of freedom. So the degree of freedom is the number of rows minus 1 times the number of columns minus 1. If you look at the table here, the number of rows, we have 1, 2, 3, 4 rows and 3 columns, P, Q, and Z. So number of rows, that's 4. So 4 minus 1. And it's 3 columns, so times 3 minus 1. So 3 times 2, that's 6. So the degree of freedom is 6. So we can go to the table, look for a degree of freedom of 6, which would be in this row. And remember, we're doing at the 5% level of significance. So if we subtract 5% from 1, that's 0.95. So we're using the values in this column. So it's degree of freedom 6, and these are the levels where the 5% level of significance. So these two colors are 12.59. So the critical value is at 12.59. So the critical value, so it's critical region, is anything greater than 12.59. We will reject the null if it's greater than 12.59. State a valid conclusion for the test given that the value of the test statistic is 81.92. So the test statistics of 81.92, it's greater than the critical region. So we'll obviously reject the null and conclude the alternate. And the alternate is that there is an association between the age of the voter and the candidate preference. Let's move on to the final question. Question 6. Define the term bivariate data. So bivariate data is data, just data involving data involving the relationship between two variables. Alright, data analyzing is a better term. Data analyzing the relationship between two variables. State 2 limitations of a simple regression analysis. So one limitation is that the impact, the influence, that's one, the influence of other variables are not taken into account, or you could say they are ignored. And 2, it cannot prove a causal relationship between the variables. Meaning, correlation, if two variables are correlated, it doesn't mean that one is a cause of the other. So it cannot establish or prove a causal relationship. Let's move on. A manufacturer stores chemicals in tanks, which he uses for making weed killers. Some of these chemicals can evaporate whilst in storage. 10 tanks were randomly selected on the length of time each was stored in the water house. T represent weeks, and loss due to evaporation represent E. These are shown in our table. So we're given the summations, and we're asked to do a scatter plot to represent the data. So we simply just plot these points. So plotting these points, I will put T on the x-axis. See, T seems to be the independent. Normally time is an independent variable. So T, we can replace T with X and replace E with Y. So Y would be the dependent variable here. Calculate the mean time that the chemical was stored in the water hose. So the mean time, let me use mean time as T bar. So mean time will be sum of T over N. The sum of T, that's 106 over N. N is 10. So that's 10.6. And the unit of time we are using is weeks. So T is in the weeks. So 10.6 weeks. So we'll do a scatter plot here. So T, time on the x-axis, and E on the y-axis. Just pause the video and complete this graph. So T goes up to 18, so we can do a 1-to-1 scale. E goes up to 96, so I'll do a 1-to-5 scale for E, and a 1-to-1 scale for T. Just realizing that a 1-to-1 scale doesn't work, so I'll do a 1-to-2. So 2, 4, 6, 8. Do a 1-to-10. I'll do a 1-to-10 scale for the vertical axis, which is E. So a graph should look somewhat like this. So I use a 1-to-10 scale for the vertical, which is what E, liquid loss due to evaporation, and time T. Time is in weeks, so something like that should suffice. So that's our scatter plot. No need to draw a line. No need to draw a best fit line when the scatter plot is done. Calculate the mean loss due to evaporation. So that's E bar is sum of E over N, and the sum of E was 704, N was 10. So 704 divided by 10, that's 70.4, and E was in milliliters. Determine the regression line of E and T for the above information. The values of A must be given to 2 decimal places. So we know normally it's Y equal A plus BX. So we are using E to replace the Y. A plus B, and we're using T to replace the X. Alright, so our regression line should be in this format. If you look at the formula sheet, the formula for the regression line, this is it. We're simply going to replace, where we have X, we're going to replace that with T, and where we have Y, we're going to replace a Y with E. So this is formula for B, it's the formula for A. Replace X with T and the Y with E. Let's do that. Alright, so we rewrite the formula. Let's plug in our values now. So N, we know N is 10. So 10 times the sum of TE. The sum of TE. So we have all our values here. Sum of TE. That's 8354. So it's 8354 minus the sum of T times the sum of E. The sum of T is 106. Sum of E is 704. So that's 106 times 704. So 106 times 704 over the sum of N times the sum of T square. So N is 10 times, and the sum of T square, that's 1352. Minus sum of T, which we have, sum of T was 106. So minus 106 all square. And all of this work out to be 3.90 using 2 decimal places. We also need A. So A is equal to E bar minus B times T bar. So E bar, we found E bar already. E bar we found as, E bar was 70.4, right? So 70.4 minus B, or B value was 3.9. So 3.90 times T bar, and T bar was 10 points. So T bar was the sum of T divided by N, which is 10. So T bar we found already was 10.6. So therefore A, calculate this, A would be 29.06. So in terms of the regression line, let me just rewrite it. So E, let me just write it up here. So E, solution E equal to A, which is 29.06, plus B, so 3.90, so 3.9 times T. So that should be our regression equation. 29.06 plus 3.9 times T. And part 4, calculate the product moment correlation coefficient R to 2 decimal places. So again, in calculating R, if we go to the formula sheet, this is the formula there for R, and remember the context, T and E. So we're using X to replace T, well, T to replace X in the formula, and E to replace Y. So I'm going to rewrite this formula, replacing X and Y with T and E respectively. So again, that's our formula. And we'll be substituting, of course, these same values in the formula. So R, N is 10 times sum of TE, that's 8354, minus sum of T, that's 106, times sum of E, that's 704, all over square root. And in the square root now we have, for the first bracket there, we have N, which is 10 times sum of T squared, that's 1352, minus sum of T, That's 106 square. Close and open another bracket. 10, which is n. So n 10, so formula is n. Well, n is 10, so 10. And the sum of e square was 53, 112. And sum of e all square, so 704 square. And we put this in the calculator, and all of this works out to be 0.99 to 2 decimal places. Interpret the value of r, calculate that we just calculated. So r, remember r was 0.99. So the closer r is to 1, positive 1, so it's a strong, positive, linear correlation between, remember what t was between t, remember t was time spent between t, and t was time that the chemical spent in the storeroom, so time spent in storeroom. And E was the chemicals lost due to evaporation. Discuss if the regression line E and T can be used to predict the amount of evaporation that would occur after 25 weeks. Use evidence that is tied to the given scenario to support your response. So the regression and T can be used to predict the amount of evaporation that would occur after 25 weeks. So remember the equation that we have that said E was equal to, the regression equation was E was equal to, what was E equal to again? 29.06 plus 3.9t. That was the regression equation. So we can say, since the correlation is very strong, the regression equation can be used to predict the evaporation after 25 weeks. And of course, we can use a formula. So therefore, E would be 29.06 plus 3.9. I remember the T represents time in a week, so 3.9 times 25. And we'll end up with 126.56 milliliters. And it's very important to point out that it doesn't necessarily mean that one is a cause of the other. We're simply basing our answer on the model and on the fact that the correlation is extremely strong. That's it. End of test.